We will wait for 2-3 more minutes and then we will start. Hi, good evening, everyone. Welcome to the tutorial session for fundamentals of MIMO communication. This is our first tutorial week. We will be discussing on the lecture that is covered in the week one, and moreover, we will see some assignments that are to follow. In this tutorial specifically, I will be discussing assignment 0. Can you please confirm if my voice is audible and there is no noise or anything?
Yes, it's audible.
Okay, thank you. So to start with, we will be first seeing what MIMO is. MIMO is basically multi-input, multi-output communication, where we have multiple transmitters and multiple receivers. So in this diagram, as you can see, wait a second, I will have to mute. Sorry for the interruption. In this diagram, you can see, as you can see, this screen is not visible. Okay, wait a second, please.
Yes.
Can you please confirm if the screen is visible or not?
Now it's visible.
Okay, sure. And can you confirm if there is some echo or anything? Nothing is there, right?
Echo is coming in your voice. Maybe you turned on
Okay.
the mic of both the devices.
No, Oh, I did not do that. Issue. I believe now the echo is not there.
No, it's there. Turn off the mic of your tab, I guess.
Am I audible now?
Ah, yes, yes.
Okay, so if there are no other interruptions, I think we will start with the class. So MIMO is like the transmitter and the receiver both will have multiple inputs and multiple outputs. So in this week tutorial, we will first go through what channel is. So as you can see here, there is a transmitter which has NT antennas, and we have a receiver that has NR antennas. Hmm. So, whatever connects these NT antennas to the NR, like these NT transmitter to the NR receiver, is the channel. So, as we can see at the output, we will have a stream of data. Uh, at the receiver, at the first receiver, we will have Y1. At the second, we will have Y2, and so on. It will be like that. So, the equivalent channel equation we can write in the MIMO as y equal to hx plus n, as it happens in case of wireless communication. So here, this at the first channel, if we can see at the first receiver, the output will be like the data is transmitted from X1 to the NT transmitter. All of these transmitters are transmitting the data, and and at the receiver, all the data are combined according to the channel coefficient. So at the first receiver, we can see that from the first transmitter, it is getting the signal multiplied by the channel coefficient that is linking the first receiver to the first transmitter. Similarly, for the X2 data stream, the channel coefficient will be linking the first receiver to the second transmitter. So this explains the number H12. This is receiver to transmitter. Always we will write it as receiver to transmitter. So for the first receiver only, the data transmitted from the NTth transmitter will be XNT, and the channel coefficient will be H1, NT. Likewise, we will write for the second transmitter, the channel coefficient would be second to 1, like second receiver to first transmitter, the channel that is connecting the next one, plus second receiver to second transmitter, X2. Likewise, second receiver to NTth transmitter, XNT, plus N2. So likewise, what will be the data stream at NRth receiver? This would be H of NR comma 1 X1 plus H of NR2 X2. Likewise, H of NR NT XNT plus noise term would be N of NR. This we can write in terms of matrix, right? We can write it easily in terms of matrix multiplication as Y1 to YNR. This would be a NR cross 1 matrix. These channel coefficients would be H11, H12, H1, NT, and here H, NR1 to H NRNT into the uh, X vector, that is X1, X2 up till XNT. This would be NT cross 1. And what would be the size of the channel matrix? This H would be NR by NT. And plus this noise term is there, N1, N2 up till NR. This is also NR cross 1 because our receiver is NR cross 1. So this we have seen in case of downlink from transmitter to receiver. Anyhow, whenever we are taking any channel matrix between NT transmitter and NR receiver, the channel matrix always will be NR by NT. Moving on, this you can see from the lecture that this new estimated 5G will be having more data rate, peak data rate, user data rate, spectral efficiency, more mobility, less latency. Likewise, this you have to see in the lectures that this has a very much of advantage over the previous previous versions. Now we will be coming to types of MIMO. So this is like now we have NR transmitter, NT transmitters and NR receivers. So this may be clustered or may be distributed. So in the first case, we are saying that we have a transmitter that has NT antennas and NR receivers. So this channel would be like each antenna connected to the each antenna from the transmitter side connected to each antenna from the receiver side. So this kind of configuration will be called as single user MIMO. After that, the second case is when we have clustered antennas at the transmitter but distributed antennas but distributed user side. So here we are taking one single transmitter with NT transmit antennas, and we have NR different users each with single antenna. So these are NR users each with single antennas. This type of distribution is called as multi-user MIMO. Then the third type is this is point-to-point transmission, but multiple transmitters are there and multiple receivers are there. So this in this configuration, we have NT transmitters of single antenna, and we have NR receivers of single antennas. So this is the type. The second type is the one that we use most commonly for MIMO. Now,
Hello,
so
yes.
suppose, yeah, hello.
Yes, yes, continue. Please continue.
Oh, sure. So now when we talked about channel, the big question is that what kind of channel we are looking at. What is the property of channel? What is the characteristic of channel? So channel depends upon what is at the input side and what is at the output side. Now at the input side, if we see that components are there, like suppose here we have input waveform, then we are passing it to a sampler, then we are again passing it to quantizer, and then encoding happens, and then if we say the channel is transmitted, and then at the receiver this channel is decoded, then the reverse operation happens, lookup table is there, analog filter is there, and then we are getting output waveform. So if we say that after encoding channel is transmitted, there will be more components after this also. This encoder is also comprised of major different blocks. But if we say that after encoding, this is transmitted to the channel. So what we will see channel as that what is transmitted and what is received. This will be the type of channel. Like suppose encoded version of signal is transmitted, and then it is coming to the receiver, and then it is getting decoded. So what will be the type here? Binary signal is transmitted and binary signal is received here. So this type of interface, this will be a binary type channel. Then if we see here, if we say that no, we are not seeing this encoder right now, we will quantize and then we are transmitting the channel. Obviously, it is getting decoded, but encoded and decoded, but we are not considering that. We are just checking after this. So after quantization, we will have these symbols going in and these symbols coming from the channel. If we consider this interface to be the channel, so this channel would have this symbol sequence. So now if we say no, we are considering this interface as the channel. This part we are considering as transmitter and receiver, and anyhow this like each block at the transmitter has its opposite block at the receiver. So we are suppose we are taking this interface as the channel, this after sampler. So here this after sampling this analog sequence is there, and after lookup also analog sequence is coming. So this type of this type of interface will be analog. But if we say that this source coder block is there, source encoder, source decoder, now we consider these two. I'll describe it in more detail. So what happens at the encoder is that at the encoder packets will go in. After that CRC will happen. Then here it is forward error correction, interleaving. Then we have symbol mapping. Then D2A converter. Then RF amplifier. And then we are sending it to the channel. At the receiver, this is received, and then this is RF receiver. Then opposite it will happen, analog to digital. Then opposite of this will happen. We're not going into the details, but this will give you a basic idea of how are we defining the channels. Then here decoder will be there. Again here CRC check, and packets are received. Now this I have zoomed in for the source encoder and decoder only. This, as you can see, is comprising of many other blocks. Now if we say that after RF amplifier we are considering this channel. So this channel will depend upon what carrier frequency. Before this we were not seeing the carrier frequency, but if we are taking this interface as the channel, then we have to see this will be the RF channel. Now suppose that we are taking this interface as the channel. So at this interface you will see here we have converted digital to analog. So the signal entering here is analog signal. Signal coming here is analog signal. But carrier frequency is not there because we have eliminated this RF component. So here it adds carrier frequency and here it will remove. So effect is anyhow nullified. So here we can say that it is baseband analog channel. Now if we take this interface, So what is happening here is that symbol is getting mapped and here it is getting demapped. So some discrete samples are there which are coming and going. So symbol mapping, what I mean is constellations like OM, QPSK like that. And after that, this is also like this. So here, this will be a discrete channel. Like suppose we are transmitting some symbol, constellations are there. So suppose if we are transmitting QPSK signals, it will be some fixed point in the constellation. And here when it comes back from the channel, we assume that some noise has been added and then the points are shifted somewhere here, or something like that. Now you can see that the mostly what we use in our communication system is this model only, right? We're considering channel from here only, and after coming back, noise is added and then symbol gets shifted like that. Now again we consider this one. This one is like binary input, binary output. So this is again binary interface. And here packets are there. So if we check for the performance here it would be like the performance metric would be probability of error. Right. Here also it will be probability of error, but this will be different from this one. So likewise, this will give you a basic idea of what channel is. So how are we designing the channel? Why we are not taking FC, because we are not considering this channel. We are not considering the carrier frequency in our communication system that we are discussing right now. So I hope this gives you a basic idea. Afterwards, there are some types of channels like we discussed. So more details you can see in the lectures, but some of these concepts will be important in solving the assignment. So there will be some types of channel. Some are like binary channel, then symbol channel that I discussed, that is MRE channel. Then there will be AWGN channel. Then some channels are non-ideal channels. And this some LTI channels are there. Linear time variant channels. This channel is mostly used in wireless communication. AWGN channel we have already studied in digital communication. Then there are non-linear channel. So I think this much basically describes what is being taught in the week one lectures. So now we will move on to the assignment zero questions, that some questions I have picked in from. So here we are checking entropy of two symbol source with symbol probabilities P and 1 by P is maximum when P is. So how do we define entropy? Like if we have a symbol source X, it consists of two symbols X1, X2. Then how do we define the entropy? Two symbols are there. These symbols will have their own probability P1, P2. You consider n symbol source. The symbols will be X1, X2 up till Xn. Each one with probabilities P1, P2 up till Pn. So what will be the entropy for this n symbol source? As we know, entropy formula is summation I equal to 1 to n Pi log to the base 2 of Pi. So here, if two symbols are there and the probabilities are P and 1 by P, the entropy would be minus of P log to the base 2 P minus of 1 minus p log to the base 2 of 1 minus p. So, how do we find the maxima? We are trying to find the maxima. We are trying to find the p where entropy is maximum. For the maximum entropy, what we will do is that we will differentiate it with respect to p. So now when you differentiate it, it will come as minus log to the base 2p minus of p into 1 by p into log to the base 2e term will come, and then there will be this term plus log to the base 2 1 minus p, and then one more term will come. So this and this will get cancelled basically. So what you will get is that log to the base 2 of p is equals to log to the base 2 of 1 minus p. And since log is an increasing function, we can directly write p equal to 1 minus p. So our entropy will be maximum when p is equal to 0.5. If you go and look at the textbook, the entropy curve is like this. So this attains its maxima at p equal to 0.5. I hope there are no doubts, and even if you are missing this class, this recording will be uploaded. So that's good. We will move on to the next question. So here the symbol rate of k-bit constellation is given as S, and then the bit error rate is asking. So first we see how a symbol is formed. Like suppose we have a symbol, let's say X. This X we can write as B1, B2, and so on up to Bn. Matlab, this symbol is collection of these bits. Like suppose for QM you can write as in constellation you take 00110 like this. So these are symbols which are group of 4 bits like that. So if any of the bit is in error, that symbol is in error. So that's why approximately this suppose there are n number of bits, or suppose there are k number of bits, and the bit error rate is PB. So we have the symbol error rate as k times of PB, because if any of the bit is in error, the symbol is in error. So from here we can find that PB is equals to PS by K, that is S by K. This answer is D. Here it is 0.5. Now this block diagram you see, this block diagram is for the source coder, as we have seen before also. So there is an analog source which is going to the A to D converter, and after that this block is there, and then encoder. So what happens in source coding is that some analog waveform is there. After that it is sampled. That is, it is multiplied by a train of impulses. So after sampling, we will get these equally spaced signal at so this is the sampling step. After sampling, we are getting these symbols. Now, what we have to do is to quantize. So, in quantization, what we do is that we set some threshold level, and according to that threshold levels, we will assign these symbols which are at random amplitude. We will assign them to some of our known, like we will take a symbol set, and then we will take this finite set, and then we will assign these values to that finite set. Like suppose if I am taking this, this is 0, this is 1, this is 2, and this is 3. Now suppose uh, if if the if the symbol value is in between 1 to 2, like, then we have to assign it as 1. If it is greater than 2, we have to assign it as 2. If it greater than 3, we have to assign it as 3. So what will be the quantization output? The first symbol we can see is in between 1 to 2. So it will be quantized as 1. Afterwards, the second symbol is approximately 2, a little bit more than 2. So it will be quantized as 2. Now we have 3 quantization levels, 1, 2, and 3. So this will be quantized to 2. After that, this one, you suppose that it is little bit greater than 3. So this will be quantized to 3. So likewise, what we are doing is that this symbol set we are converting into some finite symbol set that we know already. This is known as quantization. So after quantization, this encoding happens. Like suppose 3 levels are there. How do we encode these 3 levels? Like suppose we are encoding this as 0, 0, this is 0, 1, 1, 0, this is 1, 1. So 4 levels these are. So whatever here we obtained after quantizer, these we can easily encode. So what is the missing block in the following block diagram? There is the quantizer. So D is the correct answer. So the next question is the job of a source coder is.
Ma'am, I have one doubt. In the
Yeah,
last question,
yeah,
can you scroll down? Now, this is an analog to digital converter. So, like if we do sampling, so the sampled signal is not just a digital signal; it's in discrete time. So, if we are saying it's a analog to digital converter, so that means quantization is already happened because quantizer will give a digital signal.
yeah, yeah, correct, correct, correct.
So,
So here it is this one is analog to discrete signals only.
okay, okay,
After that, it is passing to the quantizer.
okay.
Okay, we will move forward. The job of a source encoder is. So, as we see in the previous question, this whole block diagram is of source encoder. So, we are taking some source and we are giving the output as bits or symbols. What is the criteria for giving the output as bit or symbol? If we are converting something to bits or symbols, the main thing should be that it should be efficient. Like suppose we have to encode, suppose 3 levels are there. So I can suppose this is A, suppose this is B, suppose this is C. We have 3 levels. How many ways we can encode it? Infinite number of ways. I can say this is 0, 0, 0. I can say this is 1, 0, 0. I can say this is 1, 1, 0. Or I can say this is 0, 0, 0. I can say this is 1, 0, 1, 0. I can say this is 1, 1, 1, 0. Or I can say this is 0, 0. This is 0, 1. This is 1, 1, suppose. So what we are considering is that the number of bits per symbol is less because we don't want to spend more bandwidth in encoding. We don't want more number of bits to spend in encoding. So what we want is the number of bits per symbol is least. So from this concept, you see what is the job of source coder. It converts source symbol into bits, that is correct, but it is representing an input source message in the most efficient way possible. So this would be the answer. Any doubt here? So next we will move on to the next question. So till now we were on the encoder. Now this is a channel capacity. So what happens is at the transmitter we have a source coder, and then the job of source coder is that it has to introduce redundancy so that the error is less. Like suppose we have two bits 0 and 1. If they are transmitted like this, so little bit of noise and the bits can get flipped. So if we are transmitting 0 1 and if we are receiving an output of 1 1, so this bit is in error, but it is very difficult to diagnose because suppose the transmission is in stream 0 1 1 0 1 1 and 0 0 like that. 1 0 1 0 1 1 0 0 like that. So if single bits are there, it is very difficult to identify if it is in error or not. So like suppose if we are transmitting 0 as 0 0 0 and 1 as 1 1 1. Now if single bit is in error, even if single bit is in error, that 0 0 0 can be obtained as 0 0 1 1 0 0 like that. So we can now judge that okay, so one bit is in error, it must be 0 because majority of bits are in 0. So this we can receive as 0. Similarly for 1. So this is the job of source encoder. What channel encoder does is that so this so this is the job of source encoder. And one more thing I forgot to discuss is that okay, uh, here suppose we are transmitting 0 as 0 0 0. So what is uh, the cost? What is the price that we are paying? The price that we are paying is that we have to transmit 3 times much power, correct? And if suppose we are saying that at the input power is constant, then what will happen is that each bit will be getting 1/3 of the power. If each bit has 1/3 of the power, that is like more prone to noise. But then it is said to give like better performance. So this is one of the good source encoding. So now we will move on to the Shannon capacity. Shannon's capacity is like the maximum information that can be sent over any channel. So till now we are like doing coding, source encoding. We are doing channel encoding, just to decide that uh, just to reach to the Shannon's limit. So the capacity is the channel capacity is the maximum permissible rate at which error-free transmission is possible. So here for this question, A would be the answer. Moving on to the next question. For Wi-Fi, the mode of transmission is. So for Wi-Fi, what happens is that the data is transmitted and received into packets. So it is like some data is there, there's some header, and then there will be some data. So what happens in packet data is that this data sliced into smaller chunks. So if uh, this is the case, so suppose one packet is in error. If it is identified to be in error, then it can be retransmitted. So that is why it gives higher data rate. So Wi-Fi is bursty mode of transmission. Now coming on to the other questions that are from the linear algebra. So this is very basic question. The rank of this matrix we have to find. So what are the approaches to find rank of the matrix? The most commonly used approach is that we have to use the row echelon form or reduced row echelon form. So this matrix is here. Here you can see that this R2 is dependent on R1. So we can easily write R2 is R2 minus 3 R1. So this is 1 0 0 then. So from here you see that no other this is possible. No other matrix manipulation is possible. One row is 0. So for this matrix, the rank is 3. But for your better understanding, I will briefly explain that what you have to do in the row echelon form. So for the row echelon form, first thing is that this 0 row, all 0 rows should be at the bottom of the matrix. And second thing is that the leading entry of each non-zero row will occur to the right of leading entry of previous row. This means that suppose for the first row, we have a non-zero term, basically 1 if we go to reduced row echelon form. Then all the other rows below this column should be 0. The next non-zero term should be to the right of this one. Then the third thing is that I mentioned currently, that leading entry of any non-zero row is 1. The next thing is that all column entries below 1 are 0. So what would be the priority is that first you start with choosing a pivot. I'll explain how it is done. So, okay, sorry, this one is the previous one. So this is our A matrix. We will start from here. Choose this entry as the pivot one, and then we will try to make it 1. So for that, what we need to do is that first we will do we will replace R1 by R1 divided by 3. So this would give it as 1, 4 by 3, 1 by 3, 2. Then the second entry is same, 12, 3, 18, 8, 2, 6, 4, 1, 5, 7, 4. Now we see this point, all columns and all column entries before 1 are 0. So for these three rows, R2, R3, R4, the first element of first column you should make as 0. So the appropriate manipulation would be R2 should be replaced by R2 minus 9R1. R3 should be replaced by R3 minus 8R1. R4 should be replaced by R4 minus R1. So that I think this will finally give this matrix 1, then 4 by 3, then 1 by 3, 2, 0, minus 26 by 3, 10 by 3, minus 12. Here we have replaced this row with this row because the second pivot is coming as 0. And after that, same method you apply. First, we have to make this one entry as 1. After that, make all the elements below this term as 0. After that, we have to choose the third pivot. And this third pivot is 0, so we will replace this R3 with R4. And then we will follow the same steps. So the reduced matrix will come as 1, 0, 10 by 30, by 30. So I encourage everyone to to just go and try it on your own. And from here we see that one row is 0. So rank we have as number of independent rows, or that is equal to number of independent columns. So here in this case, rank is 3. Please ask if there is any doubt in the row echelon form. Although this is pretty basic, but I have explained because this is a very important concept. Then the next one is maximum eigenvalue of this matrix given below. So how do we find eigenvalue? The characteristic, we have to look at the characteristic equation of the matrix. This is given by determinant of A minus lambda I equal to 0, where lambda are the eigenvalues. So we do this, and the roots of the characteristic equation give the eigenvalues. So I'll try to solve once. It would be one of the many mistakes that people will do is that they will think that sum of eigenvalues is the trace, and then trace is 5. So any value less than 5 would be the eigenvalue. No, this is not correct because eigenvalues can be negative also. So please keep that in mind. So a minus lambda we will have as minus 1 minus lambda, 3, then 5, and 6 minus lambda. Determinant of this equal to 0, we will equate. And then we have lambda minus 6 into lambda plus 1 equal to 0. So this is the equation that we will be getting after solving this equation. This one will give two values of lambda, as it is a quadratic equation. One value is I think 2.72, other value is 7.72. This is 2.27 or 2.72, I'm not very sure. So from here we can see that the maximum value is 7.72. So for this question, A is the answer. Moving on to the next question. If the Nyquist sampling frequency for a signal with frequencies is given as minus 2 Hz to 2 Hz. So we know from the sampling theorem that Nyquist frequency is more than equal to 2 times of f max. So from here, the maximum frequency of the signal is given as 2 Hz. So the Nyquist frequency would be 2 into 2, that is 4 Hz. So the Nyquist frequency is important for reconstruction of the signal. If we sample a signal at the Nyquist rate, then only we are able to reconstruct the signal. I hope this much is clear. So if the signal has a maximum frequency of fs, then if you sample it at the rate of 2fs more than or equal to 2fs, then this would be the Nyquist sampling criteria. The signal would be easily reconstructed. Then the number of bits required for representing the symbols belonging to 64 coin constellation. What happens in any coin is that suppose we have this 64 coin. First, we can start with the 16 coin. So coin is quadrature amplitude modulation. So here the signals are modulated in terms of amplitude in phase as well as quadrature phase. So for 16 coin, we would have 16 levels in phase -1, -3. So the +1, +3, -1, -3. And then on the quadrature side, it will always also be 1, 3, -1 and -3. So we get 4 symbols in each quadrant. Now we encode these symbols. So if we are getting 4 symbols in each quadrant, so total number of symbols is 16. And then how many bits we would require to encode? This would be 4 bits, because 4 bits will be giving 2 to the power 4 symbols, that is 16 symbols. So here we will use it at 0, 0, 0, 0. Like this we will do 0, 0, then 1, 1, because we will be doing gray coding. And then likewise we will do for each quadrants. Like 0, 1, 0, 0, 1, 0. Then similarly for these two also 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 0. And then what is remaining is, I think 1, 0, 0, 0, 1, 0, 0, 1. This is done in the way that each adjacent symbol is having one bit difference. So I think this should be 1, 0, 1, 1. This should be. You can look up to any textbook for this. So the basic point is that uh, we have to use 4 bits for the coding of 16 symbols. So if we have 64 symbols for a 64 coin, how many bits we would use is up to the power 2 of 64. That is 6. So the answer is 6. Here, if any m coin is given, then number of bits required to represent the symbols this would be log to the power 2 of m. Now we will move on to the next question.
And it, I guess, a seal of log to the base 2 m, seal of log, because it may be in points also, no?
Yeah, it would be C log log to the base 2m, but practically for the transmission we are using the quams which are already like to the power of 2. So yeah, that is correct. C log log to the base 2m. Thank you for pointing that out. Now we have this expression for covariance between two random variables. So the formula for covariance of any two random variables is covariance of xy is written as expectation of x minus mu x into y minus mu y. And we know what mu x is. Mu x is mean of x, that is expectation of x. Mu y is mean of y, that is expectation of y. So here we can write covariance as expectation of x minus, again this is expectation of x, times of y minus expectation of y. So we will multiply it inside. This will be xy minus y times of expectation of x minus x times of expectation of y plus expectation of x into expectation of y. Now we know that expectation is additive, so we can take it inside. This will be expectation of xy minus this expectation of x is already a constant, so we can take it out. So this would be expectation of x into expectation of y. Again here, this expectation of y is constant. So constant expectation of any constant is that constant itself. So here we can again write it as expectation of uh, x into expectation of y, and then again this term expectation of x into expectation of y is a constant. So we will write it again as expectation of x into expectation of y. Now you can see here that this term and this term gets cancelled out. So what we have is expectation of xy minus expectation of x into expectation of y. This is the variance of xy. I hope that is clear. So which option is correct? A. Now this is another question from linear algebra, which is very interesting question. Null space basis vector is asked. So first we will define null space. For any matrix A, null space of A is defined as set of all vectors x such that A into x is equal to 0. That is, now is null space unique? No. So here, as we see, this A matrix is 2 by 2. So the x would be 2 by 1 vector. So we take x as x1 and x2. Now, according to the definition of null space, we should have A times x is equal to 0. So A is 3, 6, minus 9, minus 18. X is x1, x2 is equal to 0. This will give two equations. 3x1 plus 6x2 equal to 0, and minus 9x1 minus 18x2 equal to 0. Both of which mean x1 plus 2x2 equal to 0. So best approach is we will see the options. Which one option is satisfying it? Option A is satisfying it. So A is the answer. Otherwise, you can assume x1 and x2 as anything. Like suppose you take x vector as minus 2 and 1. Is it satisfying? Yes, it is satisfying. Now the option A is what? This is the unit vector 2 by square root of 4 plus 1 and 1 by square root of 4 plus 1. That is minus 2 by root 5 and 1 by root 5. So this is the answer, but what I was trying to point out is that suppose if this Ax is 0, so is null space unique? No, null space is not unique because any multiple of x will be satisfying this Ax equal to 0. Suppose in terms of x, we have y equal to lambda times x. So according to the null space criteria, a times of y should be 0. And if we put the value of y, a times of lambda x, this we are trying to find out. So since lambda is a constant, we can take it outside. This is lambda times of ax. So ax is 0. So if we have a multiple of x also, then it will be a null space. So if x is null space of A, then y equal to A times y equal to lambda times x. Any scalar multiple of null space is also a null space. And since in the question basis vector is asking, so that is why we had to transform it into basis. Now I hope that is clear. We will move on to the next question. The determinant of the following matrices. This is a very common question, so I hope you will be able to get it. For any 3 by 3 matrix, the determinant is like, so you can write it as this term into determinant of this matrix. 6 times of minus 3 plus 5 times of, it should be 9, then plus 2 times of 7 minus 3 minus 10. So this is minus 18 plus 45 minus 20. This gives you 25 minus 18, that is 7. So the determinant of the following matrix is 7. Now the next question is Fourier transform of a rectangular pulse. So if we have a rectangular pulse that is from centered at 0 and it goes as minus tau to tau, or you can say as uh, it goes from minus tau by 2 to tau by 2. And the magnitude is 1. So this rect pulse is defined as rect of t by tau is 1 for when t is mod of t is less than or equal to tau by 2, such that t is from minus tau by 2 to tau by 2 and is 0 otherwise. So from the definition of Fourier transform, what do we have? So for this pulse, Fourier transform would be, suppose we call it as phi of tau by tau, t by tau. So Fourier transform of phi would be equal to integration from minus infinity to infinity. X of t e to the power minus j omega t into dt. So from here we can see that the pulse exists in what time domain? minus tau by 2 to tau by 2, and the pulse magnitude is 1. So 1 into e to the power minus j omega t into dt. Then we integrate it. So we obtain e to the power of minus j omega t upon minus j omega, and the limit will go from minus tau by 2 to tau by 2. So we can write the x omega as e to the power minus j omega tau by 2 minus e to the power j omega tau by 2 upon minus j omega. So we can write it as e to the power j omega tau by 2 minus e to the power minus j omega tau by 2 upon j omega. Now, this we can write it as tau by 2 in the numerator and denominator, and then e to the power of jx minus e to the power of minus jx divided by x. We can write it as sine of x. So we will have it as sine of omega tau by 2 sorry, this is 2. So we will have it as sine of omega tau by 2 divided by omega into tau by 2. So we can write it as tau times of sinc of omega tau by 2. So always the rectangular pulse's Fourier transform is a sinc pulse. So here the answer is C. Now coming to this question, this is pretty much explained in lecture 1, I think, in the evolution of communication. So initially, when 1G was there, then it was using analog communication. Then we moved on to 2G. Then from 2G to 3G, 2G had better uh, data speed than 1G. And then we moved on from 2G to 3G. In between, there was a 2.5G where we introduced GPRS. And then from 3G to 4G, we moved. Now 4G to 5G. And now we will be going towards 6G. So 2.5G GPRS was introduced in 2.5G. After 4G, MIMO was introduced. So analog communication 1G is used. 2G was not developed for voice and data communication. Data communication was added in 2.5G when GPRS came into existence. So GPRS is also known as 2.5G, is correct. Then MIMO was introduced in 3G. No, 3G just had voice and data, both through the same channels. After 4G, we started introducing MIMO, and in 5G, massive MIMO. So MIMO was not introduced. Massive MIMO is not used in 6G. There is one fault here. MIMO was introduced just after 3G. So at the time when 3G was getting used, then we started using MIMO. So this fourth one is also correct. So from here we can see that B option is correct. 1, 3, and 4 are correct. So these are the questions from assignment 0. I think assignment 1's deadline is tomorrow. So we will be discussing assignment 1 in detail in the next tutorial session. So I will give a brief review of what was taught today. So we started with MIMO. What is MIMO? Then what a channel is. Then we introduced the multiple transmitters and receivers. And we saw how the signal is getting received at the multiple number of receivers. Here, if we see this signal over any of the receivers is the sum of the signals from all the transmitters multiplied by the respective channel coefficients. So for every uh, MIMO system that has NT transmitters and NR receivers, the channel matrix will have the size of NR cross NT. So this is one important takeaway from this lecture. Then we moved on to the types of MIMO. There we have either clustered antenna transmitter and receiver, or clustered antenna transmitter and multiple receivers, and multiple transmitters and receiver. This by far is the most complex system, and this is what we are using in the wireless communications. After that, we describe that channel depends upon what we like to see. Like suppose if we are considering channel from encoder to decoder, so binary data will go into the channel, and then binary data will come from the channel. So that kind of channel is binary channel. Binary channel is also of two types: binary symmetric channel, binary erasure channel. That and all you can go through the lecture slides, and if you have any doubt we can maybe take it in the next class. Then we saw that this is the source encoder. The headline. Here also we described what kind of interface we are having at the different stages. Like here, if we see here, it will be packet data rate. Packet errors will happen. Here, binary errors will happen. Here, errors will happen, but this will not be binary. This probability of error will be different from this probability of error. And then, if we require to model the carrier frequency, then we need this channel where there will be the RF components. So this will be the RF channel. And if we don't need, then we have a baseband analog channel. So one important thing is that we, in our future studies in the communication system, we are not considering this uh, carrier frequency, because what we are assuming is that if carrier frequency is getting added, this is the RF amplifier stage. Then at the receiver, the RF, the frequency component is removed. Suppose we are transmitting xt. So if it if we are considering the frequency component, what is getting transmitted is xt into e to the power minus 2 pi fct plus some phase difference would be there, and then this would be getting multiplied by the channel, and then some noise will be added. But then at the receiver, when this is received at the RF receiver, it does the opposite. That means it will multiply the signal by e to the power 2 pi fct. So this would be h into xt to the power minus 2 pi fct plus whatever it is. So at the receiver, what we will obtain is not consisting of this frequency. So the signal that we are getting is like any constant multiplied by xt. So that is why whenever we are transmitting to the communication system, we are not considering that the signal is getting transmitted in the passband. We are always assuming that the signal is baseband. Now coming to this stage, this discrete channel that we are taking, uh, this will be requiring the major of our study. That this would be the channel that we are taking here. Symbols are going in, and the symbols added with noise are coming out. Like suppose we have to transmit some BPSK is there. So BPSK, what do we do in practice? We take two symbols, or we have the symbols, and then we are mapping these symbols as -1 and 1. And then what we say is that these symbols are transmitted to the channel. When we say that these symbols are transmitted to the channel, we are essentially not considering all these components. Then we are taking this interface, this interface that I mentioned, discrete interface. This we are considering as the channel. So then at the receiver, some noise would be added. So suppose if -1 and 1 are transmitted, what we will receive is, suppose it is 0.957 and then 0.8, whatever it is. And then we make decision depending upon this. Similarly for QPSK or QAM, I say. So we see the constellations. These are the symbols, suppose. So what do we say is that we are transmitting these symbols over the channel. What actually happens is that all of this gets followed. But then at the receiver, we are doing opposite of whatever is being done at the transmitter. So we do not bother about that. We give symbol and then we receive symbols. So suppose this TPSK is there, -1 plus I. This would be this would be 1 plus I. This would be -1 plus I. This would be -1 minus I. This would be 1 minus I. So what we are saying is that these symbols are getting transmitted. So suppose if I am saying that x1 and x2 are two symbols that are getting transmitted, I will write it as this. X1 and x2. So we suppose if we are saying that x1 and x2 belong to the QPSK constellation, and we are transmitting x1 and x2. So it can be any of these symbols. Let's say 1 plus I and -1 plus I. Now we say that this is getting transmitted. So this will go to the channel and noise will be added. So essentially, these and all steps are getting followed. But at the receiver, everything is the reverse of everything is happening. So we don't bother about that. So we just say that we are sending these symbols and we are receiving the noise added symbols. So in this case also, it would be like suppose 0.7 plus 0.5i and -2 plus 3i. Suppose this we are receiving. Now our received symbol is, the first symbol would be in this quadrant, but it will be 0.7 plus 3i. So if this is 1 plus I, so it will be somewhere around here. This is the received symbol. And the second symbol that was originally minus 1 plus I, now this would be minus 2 plus 3i. So this is going around here. What do we mean by this is that some noise is added into the symbols. So after that, we do the decision decoding that if the symbol lies in this quadrant, then it will be, if the received symbol is in this quadrant, first quadrant, then the first symbol will be decoded. Then if it is in this quadrant, then this symbol will be decoded. That is like with these and all you must have done in digital communication. So this is the concept of channel. So this is a binary channel. Binary channel also has two types. Binary symmetric channel we all have studied for gate. Then we have binary erasure channel. So these are waveform based channel. And these ones are probability based channels. Okay, so after that, we discuss some questions related to assignment 1. So I hope all of that is clear. Here also, one more thing I would like to explain is that here, whenever we are doing source encoding, we have to see that the encoding is cheap. Like we are not utilizing so many of bits during encoding. So here, suppose 3 bits are getting used, and here 2 bits we can manage. So always we will see if the bits per symbol are optimized, then that method of coding is better. Many source coding theorems are there, Shannon. Coding and other codings are there. So maybe you can go and have a look at that. Channel capacity is the maximum possible rate at which the transmission is possible. And in Wi-Fi, the transmission is burst. Then this row echelon form, row reduced echelon form, all the steps are here. So maybe you can go through it, and I would highly encourage that all of you should practice these questions before going on to the next lectures. So these are the prerequisites. So you have to be very clear in all that. So solve these questions. We describe the Nyquist sampling criteria. Then we describe the constellations, QM constellations and covariance. Then we define the null space. Important thing is that null space is not unique. Null space, that any scalar multiple of the null space is also a null space. And here the basis vector is there. That is why we have transformed it into basis. Then the determinant and all are very easy questions. The Fourier transform, I would encourage to go through it. And then this you can find in lecture 1. Everything is very much described in terms of uh, tables and graphs. Everything is given. So I would highly encourage you to go through all this. So I think that's it from my side for the tutorial 1. So in case of any doubt, please ask. Otherwise, maybe we can wrap it up. And I will be uploading these lectures to my YouTube channel. And then we will be sharing the link. So don't worry about that. Okay, thank you, Disha. So we will be wrapping up with the session for today. Thank you for joining. If you haven't done, you can anyways go back and look at the lectures. So, okay.